Alright, in this video I will be going over the composition of functions. This is for section 2.3. And we're going to start though by extending our discussion on the domain of a function that's in equation form. So we've discussed this before. The implicit or implied domain of a function includes all values of x for which the outcome is a real number. So with linear functions, our domain is all real numbers. Quadratic functions, same thing. And in fact, the only function that we've worked with so far that had a restriction was a rational function, and that's going to have a domain of all real numbers, excluding any values of x that cause the denominator to equal 0. So for example, if we had f of x equals x plus 2 over x minus 5, in this case we could never plug in 5 for the function. We never could have that as an input because it would cause our denominator to be 0 and we'd be undefined. And so the domain would be all real numbers except for 5. We'd say negative infinity to 5, union 5 to infinity. So with radical functions, this is our new one here. It says it's going to be all real numbers excluding any values of x that cause the radicand to be negative. That's just the number under the radical. So for example, the most basic radical function is f of x equals the square root of x. And we've learned in the past that you can't take the square root of a negative number. It would be imaginary. When you're graphing, when you're working with functions, everything's got to be real numbers. And so in this case, x would have to be greater or equal to 0. If I plug in 0, I can take the square root of 0, I get 0. And if I plug in any number that's greater than 0, that would be positive. We can do that as well, and we get a square root of a positive number, which will give us a real number. But we cannot plug in a negative number there. So our domain is x is greater or equal to 0, which we would write as 0 to infinity. So when you're doing a problem like number 1 here, I need my radicand to be greater or equal to 0. X plus 7 has to be greater or equal to 0. If we subtract 7 on both sides, we get x is greater or equal to negative 7. So our domain would be negative 7 to infinity. Now it's not too hard to see if you actually start plugging some numbers in. Notice if you plug in negative 7, which is part of our domain, you'd be taking the square root of negative 7 plus 7. That's square root of 0, which we know is 0, so no problem. If I choose something bigger than negative 7, like maybe 0, notice the square root of 0 plus 7, that's the square root of 7. And we get a number that's irrational, but that is considered a real number. However, what if we pick something that's smaller than negative 7, like negative 8? If you take the square root of negative 8 plus 7, that's the square root of negative 1. And again, that's not a real number. You can't take the square root of a negative. So these are the only values that you can plug in as as an input here, and your output is going to be a real number. Alright, so you might want to try number 2 by setting 2x minus 5 greater or equal to 0, and you'll see what your domain is. Alright, so we want 2x minus 5 to be either equal to 0 or greater than 0. That means positive. In other words, 2x minus 5 is not less than 0. It's everything else. If we solve for x here, we get 2x is greater or equal to 5. Just add 5 to both sides. Divide both sides by 2, we get x is greater or equal to 5 halves. So it would look like this in interval notation. So starting at 5 halves and anything larger, we can plug that into this ration or a radical function, and our output will be a real number. If you actually plugged in 5 halves, 2 times 5 halves is actually 5. 5 minus 5 is 0. And so again, square root of 0 is 0. We're okay there. Anything smaller than 5 halves would be a problem. Like, for example, 0. Notice if you plug in 0, you'd have 2 times 0 minus 5. That's the square root of negative 5, and again, that's not a real number. That's why 0 would not be part of the domain. It's not in this set. All right, so let's move on now and talk about the composition of functions. So it says the composition of f and g denoted f of g is defined as follows. So f of g of x is equal to f of g of x. Notice it's important that you know how to say this expression. It's read f of g of x. And in fact, isn't that how we read this? So if you can read this, normally students have no problem writing what it's equal to or what it means. This means this. How do I read this? F of g of x. This is f of g of x. Same thing. So notice the g of x is the input for the f function. So for this reason, we sometimes refer to g as the inner function. That would make f the outer function. And now if you look at this diagram, it gives you a visual of what we're doing here. This is basically our domain. This would be the range for this new function f of g of x. Basically, you're plugging in x into the g function, and your output would be g of x. Then you plug g of x into f, and your output is f of g of x. So we can do this in one step by calling it f of g of x. All right, so let's go ahead and do number 3a here. All right, so the way we read this is f of g of 4. But we know how to find g of 4. We just plug 4 into the g function. So we have 4 squared minus 4 plus 6. That's 16 minus 4, which is 12, plus 6. You get 18. And so we can replace g of 4 with what it's equal to, 18. And so now notice we're plugging that 18 into the f function. So here we have f of 18 equals 2 times 18 minus 3. Well, that's 36 minus 3, and we get 33. So our final answer is 33. So if you haven't already, try B. And then you can watch the video for the solution. All right, so this would be g of f of 4. That's how we read this, and that's how we read this, g of f of 4. Now, I've seen some students that like to do this. Whoops. When they see this, this is g of f of 4. That's what this means. Well, again, we can plug 4 into the f function. So that's going to be 2 times 4 minus 3. And you get 5. So this becomes g of 5. Of course, we can plug 5 into the g function. So 5 squared minus 5 plus 6. Notice that's 25 minus 5, which is 20, plus 6. So 26. All right. Let's look at number 4. Let me just try focusing here. It looks like it's a little bit out of focus. Just give me a second here. Okay. So I would encourage you to try number 4 and then watch the video. So you might want to pause it here. All right, so f of g of negative 3, that's what this means here. And so first of all, we want to plug negative 3 into the g function. So g of negative 3 equals negative 3 squared plus 1. Be careful, that negative 3 should be in parentheses. We're squaring whatever our input is. And negative 3 times negative 3 is 9, plus 1 we get 10. And so this becomes f of 10. So now we're going to plug 10 into the f function. It's 3 times 10 minus 1. And so 30 minus 1, you get 29. Let's see how you did with g of f of negative 3. Now I like to use brackets here, but if you want, you could just use a bigger parenthesis. Brackets are just parentheses. We just use the brackets when you have parentheses within parentheses to just kind of make things stand out a little bit. All right, so we want to find f of negative 3. Well, remember, the f function triples your input and you subtract 1. So 3 times my input, negative 3, minus 1. That's negative 9 minus 1, which is negative 10. So f of negative 3 is negative 10. Let's replace f of negative 3 with what it's equal to, negative 10. So now we can plug negative 10 into the g function. Well, remember, the g function squares your input and then you add 1. So we're going to square the input and add 1. Our input here is negative 10. And so that's 100 plus 1, which is 101. Oops. And so that's our first page. Let's move on to the back, or the second page. All right, so again, number 5 is actually more practice of what we've done. Again, I would encourage you to try it. If you don't feel like you need any more practice, you can certainly skip that one and move on to number 6. For those of you that did this one, though, f of g of 12, that's what this is. G of 12, we're going to plug 12 in here. It's going to be the square root of 12 minus 3, which is the square root of 9, which we know is 3. So this becomes f of 3. And so we'll plug 3 into the f function. We're going to square that 3 and add 5. So that's 9 plus 5, which is 14. Notice here our input was 12, our output was 14. By the way, one of the things I should have pointed out on the first side is, hopefully you noticed, oh goodness, now I gotta adjust this. F of g of 4 did not equal g of f of 4. We got different numbers. Same thing happened here. F of g of negative 3 did not equal g of f of negative 3. So it's not like with multiplication where the order does not matter. In most cases, you're going to get a different answer finding f of g or g of f. All right, let's go back to where we were. All right, so here we have g of f of 4. And we know f of 4, well, we just plug it in here. It's going to be 4 squared. Let's see, f of 4 is 4 squared plus 5. And that's 16 plus 5, which is 21. So this becomes g of 21. Now notice with the g function, we're going to plug in 21 right here. So g of 21 is the square root of 21 minus 3, and we get the square root of 18. However, I would remind you that this is not simplified. When we're working with radicals, it's important that our final answer is simplified. if you had a radical like square root of 5, that's considered simplified. There's nothing more I can do. If I had the square root of 16, of course I would simplify that. That's 4. And then we have radicals like this one here. It turns out they're not considered simplified if we have a perfect square factor of this number other than 1. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so you have these perfect squares, 16, 25, 36. You should know all the way up to, let's just say, about 144, which is 12 squared, and also 121, which is 11 squared. So these are our perfect squares. So forgetting 1, because 1 is a factor of all numbers, so if any of these are factors of 18, then this radical is not considered simplified. Notice 9, which is one of our perfect squares, is a factor of 18. We could write this as the square root of 9 times the square root of 2. In fact, this is how we multiply radicals. You just multiply the numbers inside. If I were multiplying square root of 9 times square root of 2, I would get square root of 18. So we're really breaking the square root of 18 into two radicals that multiply to that, where one of them is a perfect square. And so here this is 9, square root of 9, which is 3. We get 3 square roots of 2. And so that's our final answer, 3 square roots of 2, and our radical is in simplified form. All right, let's move on to number 6. So now we're dealing with something other than a number in here. By definition, this is f of g of x. Again, that's how we read this. And g of x in this case is x minus 2. So again, the basic idea of a composition of functions is we're plugging in one function as an input into the other function. In this case, g of x is the inner function and f is the outer function. So it's that basic idea. Sometimes students will do multiplication here. We have f times g of x, we said was f of x times g of x. This is totally different. This is composition of functions. It means f of g of x, which we can write this way, and now we're going to plug in what the g of x function is, x minus 2, as an input into the f function. And so now I'm going to go ahead and write the output here for f of x. Notice whatever your input is, it's going to be 2 times your input squared plus 3 times your input minus 4. So it's 2 times the input squared plus 3 times my input minus 4. So I'm just writing this, but wherever you see an x, we're going to replace that with x minus 2. All right, so now we've got some work to do, some algebra to do. We're going to have to follow the order of operations, which would tell us to first square x minus 2. So let's multiply 2 of the x minus 2's. Of course, we're going to FOIL this. When we multiply the first terms, x and x, we get x squared. When we multiply the outer terms, x times a minus 2, that's minus 2x. The inner product is also minus 2x. And the last product, negative 2 times negative 2, is positive 4. We can combine these middle terms together. We get x squared minus 4x plus 4. And so that's what I'm going to replace this piece right here with. It's 2 times x squared minus 4x plus 4. Let's go ahead and distribute here. We get plus 3x minus 6. And then don't forget, you still have that minus 4 at the end. So we still need to distribute here. It'll be 2 times x squared. 2 times a minus 4x, that's minus 8x. And 2 times 4, which is 8. And then let's bring down the 3x. And let's go ahead and add these together. That'd be minus 10. So we're almost done. Notice we still have some x terms we could add together, and these constants, 8 and negative 10. You get 2x squared, a negative 8x and 3x gives you minus 5x. 8 and minus 10 and a negative 10 give you negative 2, which we write as minus 2. So notice, be careful here, our input was x minus 2, which was the g of x function, and our output is 2x squared minus 5x minus 2. Now sometimes students think they have some kind of equation to solve here at this point. Not at all. We have an expression, a binomial, as an input, and our output is a trinomial. And there's no equation to solve. We're done there. All right, I would encourage you to find g of f of x, and then watch the video. All right, let's see how you did. So this, by definition, is g of f of x. We're going to replace f of x with what it's equal to. So this would be g. Well, f of x is this function here, 2x squared plus 3x minus 4. So let's go ahead and plug that into the g function as an input. Now notice the g function, it takes your input and subtracts 2. In this case, this is our input, 2x squared plus 3x minus 4. So we don't really need the parentheses. You could drop them or just ignore them. You're going to have 2x squared plus 3x, and the minus 4 and the minus 2 will give you a minus 6. So here your input was f of x, or this function here. Your output was 2x squared plus 3x minus 6. Honestly, our real first input is x, plugged into the f of x function, and your output is 2x squared plus 3x minus 4. That becomes the input for the g function. All right, I'm going to go ahead and stop the video here, and I'll do a second video.